Week 10, Ceva's theorem. We'll begin with exercise 8.3.1. And in this exercise, we have a triangle ABC. We have L, M, and N that are points on the interiors of the sides of the triangle. So this is important because as we work through this week and next, talking about Ceva's theorem, we'll have certain instances where L, M, and N are on the interiors of the sides, and some where we let them go on the exterior of the sides. So for this particular proof, L, M, and N are on the interiors of the sides, and we are to prove that if the three Cevian lines are concurrent, and so as you can see on my figure, I'm letting them be concurrent at point P, meaning they all meet at point P, then AN over NB times BL over LC times CM over MA is equal to 1. So we're trying to prove that the ratio is equal to 1. So let's get started. As you can see, I've already constructed an additional line, which I haven't put into my proof yet. But that's our first step of our proof, is that we are going to construct line K parallel to BC that goes through point A on the opposite sideline. And the reason that we want to do that is we want to start constructing some similar triangles. So for instance, I would say that, let me change colors here. I would say that angle ASN is congruent to angle BCN, and that is by the alternate interior angle theorem, because I've already said that those lines are going to be parallel. I'm going to say that ANS is going to be congruent to BNC by the vertical angles theorem, and therefore, because obviously that makes this angle congruent to this angle, I can say that these are similar triangles. So I'm going to say that SNA is similar to CNB. Now you might be asking, why does that matter? Well, because once I know that I have similar triangles, then I can use the sides in ratios. And that's what we're trying to do, is come up with ratios that are going to work. So I'm going to say that AN, which is this line right here, AN divided by AS, which is this line right here, is going to be an equal ratio to NB over BC. Now I'm going to continue to do that same process. I'm going to have congruent angles, vertical angles, so forth. And by doing that, I'm going to go ahead and reveal the proof so that I don't have to mess up any of the ratios. But we just together talked about AN over NB, AS over BC, and you can see in my proof I wrote it differently, and that's okay. So AN over NB is equal to AS over BC. That's the same ratio that I have written. So by doing that same process, we're going to say that CM over MA is equal to CB over AR. We're going to say CL over LP is equal to SA over AP, and BL over LP is equal to RA over AP. So again, was that a lot of work that I kind of skipped over? Yes, but in proofs, it's best not to get too wordy. If I'm following the exact same process to show that two triangles are similar, and then using the same reasoning for showing that ratio, then you don't need to waste your time writing everything out. So here's the tricky part. So now I have all of those ratios. So now I'm saying if I take BL over LP equals RA over AP, and I divide it by CL over LP equals SA over AP, as you can see, I would have BL over LP, and I would divide it by CL over LP. And on the other side, I would have RA over AP, and then I would divide it by SA over AP, and we can see that's where we get BL over LC, and then RA over SA. Now, what I have is I'm going to take BL over LC equals RA over SA, and then I'm going to use, let's see, where's the other one? AN over NB is equal to AS over BC, and then I have CM over MA is equal to CB over AR. And if you'll note, on the right-hand side of this equation, AS and SA would cancel, BC and BC would cancel, RA and AR would cancel, so I have my ratio of 1. Since we don't have much to do in GeoGebra this week, I did assign you 4 proofs. We just went through one of the assigned proofs together. For another one, this is 8.3.3, I'm just going to give you some hints, but I don't want to do the proof with you. But I think it'll be pretty straightforward once we go through the hints. So here we have a triangle ABC with proper Cevian lines AL, BM, CN concurrent at P. And we're trying to prove that either L, M, and N all are on the interior of the triangle, so all on the sides of the triangle, or just one of them will be on the side of the triangle. So to begin our proof, I'm going to include the words, divide the exterior of triangle ABC into 6 regions, numbered 2 through 7. Let the interior of the triangle be region 1. And as you can see, I have 2 figures for you. So for case 1, we're going to let P lie on the interior of the triangle. And then you're going to use the crossbar theorem, and that's just going to be the only proof, the only hint of that proof I'm going to give you. Once you look up the crossbar theorem, I think it's going to be pretty straightforward. And then for case 2, we're going to say that P, say, lies in region 3 or 6, and you can see on figure 2, I have put it in region 6. And those regions are just created by the sidelines of the triangle and extending those sidelines out. So again, P lies in region 3 or 6. Again, you're going to use the crossbar theorem to prove what you need to prove. It's a little bit more complicated on case 2, but the good news is once you do case 2, you can just say cases 3 and 4 can be proved using similar proofs for the other regions. So that's as far as I'm going to go with you this week. Good luck on those proofs.